what are the steps involved in doing PCA? If anyone remembers, steps involved in PCA, principal component analysis. Yeah, put the link to Collab Notebook in chat box so you can follow along with me during the tutorial. Yeah, explanation. I mean, what are the steps involved in PCA? Anyone? I mean, what is the purpose of PCA? Or what's the term that we are looking at? Mm, yeah, principal component analysis. What are the steps involved in principal component analysis? You, it's for dimensionality reduction. Yes, reduce the dimensions. Why do we want to reduce dimensions? To remove unrelated features, to visualize it in 3D or 2D. There are very different use cases, right? And we also looked at partial least squares. What's the difference between PCA and PLS? Principal component analysis and partial least squares. At least this should be easy to answer. The difference between these two. There was a specific term that I mentioned. Anyone? Okay, which one is supervised and which one is unsupervised learning? Okay, PCA is unsupervised, PLS is supervised, right? Because PLS takes into account the labels also. PCA, you will only do the transformation on the feature matrix without the target or labels. Okay, this is the difference. Okay, let me share my screen. We'll go to the notebook. Yeah, my notebook is visible. Okay. Today in this session, we'll be looking at three other dimensional reduction techniques also, namely non-negative matrix factorization, T-SNE for T-stochastic neighbor embedding, UMAP for uniform manifold approximation. So these are different algorithms that will help you do unsupervised learning, dimensional reduction. Okay. I'll start by importing some packages. Okay. This is done. Some data sets, some functions, and I'm loading some data set. This is called the penguin data set. Okay. So you have four different features and three different species. Okay. Based on this information, you are based on this information, these four features, you're trying to predict which species of penguins does these features correspond to. Okay. Sure. Here's what the internet says. Our model will. Yes. Yeah, just like the scatter plot that we saw last time, the same thing we have it here. Okay, we have three different species. Okay, and four different features. Let me zoom out a bit. Yeah. So based on this plot, again, as I asked you last time, which univariate feature should I use first to have good class separation or discrimination? Just based on these four plots, let me know. Okay, I would say body mass, flipper length. I mean, uh, all four are somewhat equally discriminative. But if you see combinations, I would say combination of bill length and flipper length is good because there are three different clusters. If you look at anything else, yeah, there is some sort of body mass and bill length. Okay, there is some separation, flipper length and bill length. So again, the problem here is you can go up to three dimensions where you can look at combination of three features, but four dimensions you can't look at. Same problem that I discussed yesterday. Okay. I'm removing NaN values, meaning like missing values. Okay. There are some missing values. I don't have information on body mass for this specific penguin sample and so on. So I don't want all these. I'm removing it. Okay. And in my data set, I have three different species, Adelaide, Gentoo, and Chinstruck. These are different counts. Okay. I'll use only numerical features. I won't be using categorical features like year and gender and so on. And can anyone tell me what does the standard scaler do? Standard scaler. Okay, let me explain. Okay. You see, bill length, the range is like 30 to 60 here. Bill depth is like 15, 20. Flipper length is 175, 225. Body mass is like 2000, 6000. Okay. Typically in machine learning, let's say larger the value, you will get higher prediction and so on. Okay. To but it doesn't mean that it's large. It's large with respect to other features, but when it comes to prediction, you have to make sure that everything is in proper range. Okay. Everything is in the same range. So to do that, I'm converting everything. This is called normalization, okay, or standardization. I will convert all these values from -1 to 1 in between a range from -1 to 1. Okay, that is what I'm doing. Okay, get it? Any doubts till now? Okay, yeah. So moving on. Again, typical scikit-learn machine learning, you initialize the class that we have. Okay, PCA is the class that will do principal component analysis. And here, default n components is an argument that you can set. If n components is given as none, then it will return four components. Okay. And this is how I get the eigenvectors, eigenvalues. Okay, these are my eigenvalues. So if I want to, let's me, these are my eigenvectors, these are my eigenvalues. If I want to select, if I want to select three components, I will select the first three eigenvectors because I have ordered my eigenvectors and eigenvalues according to these values that I singular values that I got. First component's eigenvalue is 30, second is 16, third is 11, fourth is 5. Okay. And as I talk uh, about the plot yesterday, you will have this percentage, okay? Percentage of explained variance. You see, first component, first component has explained variance of around 70%. Second is around 20%. Yeah. So, and third component is around 15 and fourth is around zero point 0.1. So how many components should I select based on this plot? I want a total explained variance of about 90%. In that case, how many components should I select? How many components? Anyone? Come on, people think. I have four features. I want to reduce dimensionality. I want at least 90% of my data to be explained well. Okay, if I want 90%, I'll just take component 0 and 1, first two components, okay? And what are these components you should think like some combination of four features I'm getting these components, okay? Like some linear combination of random four, I mean first four features, I'm getting these components, one and two. You should. I mean, it might be difficult to understand, but yeah, when you read a bit more about PC, I think you'll have a better idea. But you can think of it, I'm reducing from four features to two features. Okay, that is what I'm doing. Yeah, this is the mathematical operation that I defined yesterday. This is the PCA.transform method. Okay, you can transform and let me plot component 0, 1, 2, 3, and species. This is my transform data set. And I just want component 0 and 1 to be plotted. Okay, see, does this have somewhat good separation among species? Does this have good separation of classes? Okay. There is somewhat good separation. Orange is here, blue is here, green is here. I mean, there is some overlap, but since it's only 90% variance captured, you might not see the actual separation in two dimension. Maybe in 3D you can because that will lead to like 99%. That is more accurate. Okay. But yeah, these combination of four features work. You can just take the first two features, component zero and component one, okay, and then do whatever linear regression or logistic regression, and so on. Okay, any doubts in PCA? Okay. Moving on to non-negative matrix factorization, all NMF. Okay. Again, you don't need to worry about this method. Okay. These are all some mathematics I've put in the notebook. Okay. I'm getting the data set. Okay. So I have 400 samples. Okay. And number of features is 4096. It is an image. This data set contains images of 400 people. Okay. So this is an image of one person right here. But I don't want to, have like all 4096 features. I want to reduce it. I don't want like, I want to remove features that are redundant. Redundant meaning same features again and again. Okay. Here I'm using NMF instead of PCA. I'm setting n components to be 25. Okay. It'll take some time. And yeah, dimensionality is reduced. Okay. See, these are all the different components of NMF. Based on less information, I'm trying to reconstruct whatever images that I have. Okay, these are all different faces. I mean, it might be a bit blurry, but you can see that it is able to capture the nose, eyes, glasses, mouth, teeth, chin, and so on. So the idea here is using less information, I'm able to get more faces, but I mean, somewhat similar to the original face. Okay, let's see an original image and reconstruct the image. This is the original image that I have, and this is what I reconstructed from the dimensionally reduced image. Okay, do you see any difference between these two images? Anyone? Any difference in original image, reconstruct image? You can see that there is some information lost, right? I mean, it's the eyes are not clear, glasses are not clear. You can't see the dress; it's not clear. But what we have achieved is very good compression. Okay, from 400, I'm reducing the components to 25. Okay, that's what I've done. That's very good actually. And one more thing you can do is you can also keep generating random faces using NMFC. I'm able to generate random faces also. I keep running it again and again. I'm generating different faces. So this is a new thing. I mean, additional reading I've given here. You can all go through this paper. Okay. But the idea here is I want to compress the image and reconstruct it whenever I want. That is the idea here. 100% reconstruction is never possible if you reduce dimension. But yeah, it's somewhat close. Any doubts in NMF? Okay. I've given the link to the paper and the documentation for further reading. Yeah. Uh, and okay, the next thing called T-distributed stochastic neighbor embedding. This is another version, another dimensional reduction technique. But the important thing you have to note here is it is a non-linear dimensional reduction technique. Can anyone explain what's the difference between a linear transformation and a non-linear transformation? These are all basics that you might have studied. A linear transformation, non-linear transformation, and so on. Think about it for some time. Okay, let me just type it out here. See, in PCA, what will happen is you have like one sample. Let's say my features are 1.4, 2.4, 2.5, and 2.6. Okay. If I want to get a value for the first component, I'll be like 1.2. I multiply it with some constant, say 1 plus 2.422. This is my first, this is what I call a linear transformation. Okay. This is my first component, component 0. For component 1, I'll be like 1.2 into 2. Okay. You see, what ultimately we are learning in PCA is what factor should I multiply each value with. Okay. See, for component 1, it's 4. I've learned that it's 4. For component 1, it's 5 for fourth feature and so on. These are the constants that I'm going to learn or weights that I'm going to learn. But this is called a linear transformation. Okay. In non-linear transformation, it can be instead of 4, it can be 2.6 square times 4 cube or something. This is called a non-linear transformation. This is what TSNE is learning. Okay. I'm loading something called the digits data set. Digitates asset, I have handwritten digits from 0 to 9. Okay, this is my data set. And I'm I have the image. I'm seeing how much explain again. I'm using PCA and checking explain variance. Okay, I have 63, 64 features. 90% explain variance I'm getting by using just 33 features. So I can reduce from 64 to 33. And if I go to tsne, you see, I'm plotting from 0 to 9. Okay, 0 to 9. And you can see there is good separation from 0 to 9. Zero digits are here, one is here, two is here. So we can say that tsne algorithm is able to capture the underlying distribution better. Ultimately, again, I'm saying we can't visualize in 64 dimensions. We are visualizing in 2 dimensions. There is good separation, which can say that each digit is unique in their handwriting. Okay, got it? Okay, moving on. Then other thing is uniform manifold approximation and projection. This is again a nonlinear dimensional reduction technique. Again, mm, you import the class, you have different hyperparameters called n neighbors, min dist. You again have something called perplexity. You can keep changing these values, okay, and see how the plot changes. I've shared the notebook for that case. You keep tinkering with the values and see how the plots change. Then you'll get a better idea. Okay. Okay. Again, you have to install this package in Collab, okay? That is also there. You can write pip install. If you go to Collab, what you should do is in any line, you just do pip install umap learn plot. This is what you should type in Collab. Okay. It's not installed by default. Again, I'm setting some different hyperparameters in neighbors mindest. I'm reducing the dimensions to 2 again. I'm transforming the data set and plotting it again. This is my UMAP. You can see it's different from way different from TC. There is even better separation. TC, it's like everything was nearby, nearby, nearby. Here, it's even more well separated than TC. So this might be a better algorithm for doing dimensional reduction. Land TC, again, it depends on the data set, whatever data set that you have to try TC and UMAP, and then do whatever downstream machine learning models are developed, whatever insights you get, and so on. Any doubts, people? Any doubts? And again, I've given links to further reading here. Any doubt in this whole tutorial, anything you didn't understand, please let me know so that I can give an explanation. Okay. I'll wait for some time. Go through the collab notebook by yourself and let me know if you have any questions. I hope everyone is able to run the notebook by yourselves in collab. If you run it, then only you'll get to know how everything works. What is a class? What is a method? What is an attribute? If you don't have any doubts, then I think that's it for today. It would be better if the class is more interactive so we can exactly know what to teach and how to teach. So I expect at least some participation in the next class. So yeah. Thank you for attending today's session. Thank you. Thank you.
Oh, wow.